Okay, part 2, multiplication. So, assuming that you've just gotten here from my point addition lecture, you'll remember that we were saying that any 3 points on the same line sum to make the point at infinity, which is the identity element for our elliptic curve group. Doesn't matter what elliptic curve we've got, that will always be a point on the elliptic curve, and we will just use it as our identity element since we always know that's going to be there. This is the same graph as from the first lecture, where we can see my elliptic curve and move the points around and draw a line between. That's all the same. So last time we talked about there's a special case for adding a single point to itself. So this was slightly different because my formula here breaks down when we have the same point added to itself. So here I have nearly the same point, x-coordinate 3 and x-coordinate 3.04. And it looks like I've got this tangent line going on here, but if I make it exactly the same, then my blue line disappears because my formula is undefined. So in that case, we just draw a tangent line instead. So draw the line tangent to the elliptic curve at the point P. And I have that again illustrated in this other graph. So here's an elliptic curve, here's a point P, and there is the tangent line. So incidentally, this is the reason why we exclude elliptic curves with that self-intersection, because the self-intersection point is not going to have a tangent line that we can use. It'll have 2 tangent lines, and then that just makes everything horrible to work with. But we can throw those out because those are the elliptic curves whose discriminant is 0. So very easy to test for those and just exclude them. So right, before I get too far down that tangent, as it were, we're going to take the point P. We are going to draw a line tangent to the elliptic curve based at P. We're going to find the point R where the line intersects the elliptic curve again. Negate the y-coordinate of that R because P plus P equals minus R. So in my picture here, I said this was my point R. This is P plus R makes identity, so it must be that P plus P equals minus R. So P plus P equals minus R, which is down here, right? So again, we saw this in the previous segment. So this would be my P plus P, where my mouse is about. So what I want to focus on for this lecture is that since we've got 2 copies of P and together they make the point minus R, what happens if we continue to add on more of the same point? So I'll start out with the point P. We already found P plus P, and just so I don't have to write a whole bunch of plus signs all over the place, I'm going to call this 2P, or twice P, or you can think of it as 2 copies of P added together. It's a nice thing about the elliptic curve group that it is abelian, so we don't actually need to worry about what order we add things in, because if you take 2 points and you have them in the opposite order, they still have the same line between them. Right. So if twice P is 2 copies of P added together, then I can add on another copy of P, right? This is a point on the elliptic curve. This is a point on the elliptic curve. And whatever I get out of that, I'm just going to call it 3P, right? Because I'm adding 3 copies of the point P to itself. So again, let me demonstrate this on Desmos. This is nearly the same picture as before, zoomed out a little bit. I've got the same elliptic curve as my previous graph. I've got the same point. I've got the same tangent line. But I've gone through and I have highlighted this red point down here, which is P plus P, right? So this is my point P. I add it to itself. I follow along this line and I reverse the y coordinate. So I got this point as my 2 times P. And if I want to get 3 times P, I take 2 times P and I add on another copy of P. So let me activate this formula. Now I have another line. This is now connecting 2 different points. So I need to zoom in a bit to find their intersection, right? So P, which is now off of my screen, plus 2P, plus whatever this point is, I'll call it R. They make the identity. There I can see it a little bit better. So it has coordinates 3.143 and negative 5.636. Because P plus 2P plus this point make the identity, P plus 2P makes minus this point, and that will have coordinates 3.143 and positive 5.636. I can zoom out a bit. So here was P, here was 2P, 3P is going to be back up here somewhere. It'll have the opposite y coordinate of this intersection, but the same x coordinate. So somewhere about where my mouse is. So I can keep doing this. This would be P again. This would be 2P. 3P is up here. If I wanted 4P, I would connect those by a line. It looks like it intersects somewhere on the horseshoe, which would put 4P down here. If I wanted 5P, I could draw on another line and do another intersection and do another negating of y coordinates and so on. Any number of P's that you want to add together, we can just keep on doing this. So in my notation, I'm going to keep using capital letters to indicate the points on the elliptic curve. So this P is really an XY coordinate pair that satisfy the formula for the elliptic curve. And if I need to talk about some number of copies of P, I will use a lowercase letter to indicate an integer. So I can have 1 copy of P would just be P, 2 copies of P would be 2P, n copies of P added together would be NP, or you could call it n times P, because you're a computer scientist, you don't want to get confused about that kind of stuff. But this will be the notation that I use. And again, there are formulas for this kind of stuff that I will introduce on Thursday's lecture. And we will very soon be passing all of this brute work off to computers. But the point of this material today is to understand the geometry of where this group operation is coming from. So I hope you enjoyed that, and I hope you're looking forward to some applications to cryptography. On Thursday, we will talk about implementing this using modular arithmetic for the coordinates instead of using real numbers. And we will start looking at some simple computer programs to help us make those calculations without us drawing diagrams and putting in tangent lines every single time. Great. Then I will see you again on Thursday.